So today we come to tangent spaces to a manifold, and the definitions we're going to make will be the probably single most important definitions in differential geometry, namely that of a tangent vector to a manifold and all the other constructions we are going to derive from it. Now, having reviewed last time the basics of vector spaces, and in particular having included infinite dimensional vector spaces, we are today going to make good use of that. And the tangent space to a manifold will ultimately, will be a finite dimensional vector space if the manifold is finite dimensional. It will have the same dimension as a vector space as the manifold has as a topological manifold. But first and foremost, before we come to that, we will construct an infinite dimensional vector space from a given smooth manifold, and that object will appear again and again throughout these lectures. So let M be a smooth manifold, and actually throughout this section, throughout this chapter. And I already emphasized that if I say M is a smooth manifold, it comes without saying that it is equipped with a topology in a smooth atlas. I will suppress this now in the notation, and only when several manifolds with several topologies and atlases are chosen and it becomes particularly important to emphasize the differences, then I will return to writing that down explicitly. But from now on, we're grown up, you assume this is given. So let M be a smooth manifold, then we can construct a vector space, or the vector space, over R, so over the real numbers, because we're looking at smooth real manifolds, the vector space over R, whose underlying set is the set of all smooth functions on the manifold, and it is equipped with an addition and a multiplication, an S multiplication. So these are the smooth functions, f from M to R, but they ought to be smooth. And then this plus is the pointwise addition. So whenever you have maps, you can actually define their addition. So say you have an F and a G, which are both smooth maps, and then you define this addition, which is then an addition on C infinity of M, of course, and you can define the resulting sum function as the sum of the functions. This is what you mean by pointwise if you do this at every point P of the underlying manifold. And now this here, of course, is the addition in the real numbers, because F and G send a point to the real numbers. And similarly here you have pointwise S multiplication, which is lambda times F, but this here is the S multiplication on this set, and it is defined as lambda times f of p if you evaluate this at p, and this is inherited from this from this multiplication on R. So now it's my claim that this is a vector space. It's quickly checked that this is a vector space. You believe that or you check it. It's pretty obvious. And this is an infinite dimensional vector space. But it will play an important role. Now, the central concept we're going to define is the following. Definition. Let gamma from, let's say, the whole real line into the manifold be a smooth curve. I write from the whole range R into M because I don't want to bother about what exact range, whether it's an open interval. Well, this is an open interval. You can always reparameterize and change that. It's just convenient to not have to bother about this. One could be very picky and say, well, this is just an interval from A to B, and then you always have to worry about the domains and so on. Actually, everything becomes very simple if we're a little bit cavalier here. If you wanted to have it more precise, and sometimes I might want to have it more in a more precise manner, then I will be more specific here. But let's say a curve has, for the purpose of what we're going to do here, the full real line is a parameter range. So let gamma be a smooth curve through a point P in M. So in a sense, we pick a point and we look at the curve through it. Now, without loss of generality, W log, without loss of generality, we may arrange for P to be that point through which the curve, where the curve is at parameter value 0, right? So if it's not, you can easily define a curve with a shifted parameter value such that at time, if you wish, at parameter value 0, it is at the point P. This without loss of generality, we can always arrange for this. It's just convenient to do that. Also, this could be dropped, but it makes formulae simpler. So now, if we have this situation, then the directional derivative operator, that's the full name of this guy, well, not quite, then the directional derivative operator at the point P along the curve gamma. So actually all of this belongs to the name of this object. Then directional derivative operator at P along the curve gamma is the, now very important, linear map with name X, but it depends on the curve you have chosen and it depends on the point P you have chosen. It's this linear map. So from where to where does it map? Well, if it's a linear map, it must send a vector space to a vector space. And the vector space where it starts is C infinity M. Now this is this underlying set, but because it's a vector space, I can talk about it being a linear map into the real numbers, which here, because if we want to talk about this being a linear map, we must consider as a real vector space, well, over itself, as an R vector space, R to the 1. So both of these come with their additions. This C infinity M comes with this plus in S multiplication just defined. This R is the R1, comes with the vector addition and S multiplication, which coincide with the field addition multiplication. Anyway, this is a linear map, and the linear map is defined as follows. You take a smooth function f, and you map it to f after gamma. Now what is that? That kind of guy is now a map from R to R, because gamma takes you from R to M, but an arbitrary smooth map f takes you from M again to R. So in total, this is a map from R to R. As such, we know how to build its derivative, which we denote by a prime, and that is a function, but we want the derivative at 0, which is of course the parameter value at which the curve goes through the point P, and by that, by calculating the derivative and evaluating it, the result is a real number, as it should be. Okay. Now, why is this map a linear map? Well, essentially because we take the derivative here, and we'll look into that further. So anyway, this linear map, this is the name of the linear map, is called the directional derivative at the directional derivative operator at the point P along the curve gamma. Now, there is an important piece of terminology, and that is that in differential geometry, this x gamma comma p is usually, and we will follow this convention, is usually called the tangent vector to the curve gamma at the point P in M. So there it is, a tangent vector. But we shouldn't be, by the terminology, be deluded into thinking that this is anything like a collection of numbers. Well, finally it will be, but at this point the tangent vector formally, abstractly, is a directional derivative operator. The tangent vectors are operators, derivative operators, that act on smooth functions. That is how the concept of a vector, of a tangent vector, technically survives in differential geometry. Okay? So from undergraduate physics, you have this notion that you have a vector, you have directions, and now you can, in a sense, dot them into, say, the nabla operator or something. Nabla, x dot the nabla operator, right? And that gives you a directional derivative. Now, so there in undergraduate or vector calculus, whatever you call it, in engineering mathematics, you have the concept of a direction, and then you combine it with the concept of derivative, and you get the directional derivative. Now, in differential geometry, these concepts are married to each other, but they cannot separate. Okay? There's no longer an independent notion of direction and an independent notion of derivative. There's only the combination of the two. Okay, this is very important to keep in mind because this is the key point in the technical understanding and therefore the practical understanding of tangent vectors in differential geometry. And today we'll elaborate on that and we'll find all the consequences of that. But the definition as it stands is, of course, crystal clear, like this. Okay, now, So a precise intuition is the following. A precise intuition is the following. X gamma comma p is the velocity of the curve gamma at the point P. Now, you remember that we said, given a smooth manifold, we wish to construct tangent spaces not by referring to an outside space into which we can think of the manifold as being embedded, come to that later, but we want to do this intrinsically. Now, this is exactly the idea. You have a smooth manifold, and without referring to the bulk space around it, you consider through a point a curve gamma, and one of the tangent vectors to the manifold at this point is the velocity of that curve. The velocity definitely is a vector. Well, that is how we define it here, and this is this guy. Now, in order to provide some evidence for this, of some consistency of this interpretation, you may consider the curve, let's call it delta, which is exactly the points, runs exactly through the points to which gamma runs, but it does so at double the speed. So you multiply the parameter by a factor of 2, so you run through it double as fast. That's the intuition. Now, if you now calculate what is x delta at the point P, so in particular at lambda equals 0, they both are at the point P. What is x delta P? Well, we find out by acting on an arbitrary smooth function f. It's then f after delta. You derive it and you evaluate at 0. And it's not difficult to see that this is 2 times f after gamma derived at point 0, because you get an inner derivative from here. It goes here. And of course, any other factor, 3 times, 20 times, pi times, will pull in front. So indeed, if you run through the curve at double the speed, you get double the x gamma comma p. You get a vector that's double as long. Well, that's our intuition. You run through the curve double as fast. So if this is to be identified or has something to do with the velocity, it better scale with the same factor. And in fact, it does. Okay, so that gives you some feeling. Indeed, this has to do with the velocity. But again, this is just an intuition. This is the full definition, the technical definition. Okay. Now, once we manage to construct the tangent vector, we have the important concept of the tangent vector space. Definition: the tangent vector space, TPM. Yeah. What is this? So this is the set underlying the tangent vector space. This is the set of all the x gamma comma p. So for some p in m at p in m, so at a particular point, is the set of all tangent vectors where gamma is a smooth curve through the point p. Okay, so so the intuition here is you have your manifold, you pick your point p, and now you don't only look at this curve, but you also look at the same curve through which you run at double speed. You also look at the curve at which you run, through which you run at mu times the speed, and then you get all the intuitions, you get all the tangent vectors in this direction longer and longer and longer. You can run through the curve backwards, then you get the tangent vectors in the opposite direction, but then you take any other smooth curve through this point, and if you take all the velocities of all the curves, run through at any arbitrary speed, which then makes technically a different curve because a different map from R to M, the collection of all the corresponding tangent vectors, technically meaning of all the linear maps built there, of all the directional derivatives, this is the set that underlies the tangent space. It's very simple. It's very simple. Okay, so that's this guy. Now, this is just a set. Is this set equipped with two operations, and now we've got to be careful. Equipped with, okay, we want to make this into a vector space if we want to do justice to this name. And then we need to define two operations. Again, to be careful, we first call them circ plus and circ times, okay? And the addition must take us from two tangent vectors to, well, to a tangent vector, of course, if this is the addition needs to close on the set. But I'm going to define it in a way in which it will first remain open whether the addition will actually produce, again, such an object. Okay? And it will be one of our tasks to show that it does. Okay? And an S multiplication, well, the tangent vector space will be an R vector space, so it will be R times TPM, should produce, again, an object in the basic set, but again, we'll choose a definition that's very straightforward, but for which we need to show that also the S multiplication closes, equipped with additional multiplication, defined, and now very simple, pointwise. Now, I should again say what it means here. These objects here, the x gamma p, we remember they are linear maps from the definition. Linear maps into the real numbers. Into the real numbers, that means we can take one such linear map, let's say x gamma comma p, and we can take another such linear map, call it x delta comma p. You see, two different elements in here must come from different curves gamma. Well, so I call the second curve delta, okay? And I can define this sum by evaluating this on, well, on a smooth function f, because these guys, so I emphasize it here again because it has gone, x gamma comma p is structurally a linear map from C infinity m to R. So I can define the sum by telling what new map this is supposed to be. Well, this is supposed to be x gamma comma p applied to f, or just on f, it depends on how you denote it, plus x delta p applied to f, and this plus is just the plus in the real numbers, because the x gamma p sends you there and the x delta p too. So it's no problem to define the addition of vectors because it maps into the real numbers, and on the real numbers you know an addition. That's very straightforward, and I'm not going to write it down. Exactly the same happens for the S multiplication, only that you have a lambda here in x gamma p. You again reduce this to the definition of the multiplication in the real numbers. Now you say, okay, there it is. You have the addition, and there you are. Well, not quite yet, because we need to ensure, and this is the question here, we need to ensure that the result is again in TPM. Now, the sum of two maps, right? The sum of two maps is again a map of the same type. That's not in doubt. But this only takes care of the definition up to here. If you really look at this, you're going to say, hang on, but it's not just any linear map from C infinity m to R, but it's a linear map that has been constructed from a curve through the point in a very specific way, namely in the specific way that x gamma comma pf is actually given as the f after some gamma derivative at 0, which means we need to find for this sum, we need to find the underlying curve that produces this tangent vector. Okay, so the question is, does there exist, I've got to be very careful, this is not a formal symbol, it's, does there exist a curve sigma, like sum, such that the sum can actually be written as the tangent vector to a curve sigma evaluated on an arbitrary smooth function f. Only if such a sigma exists can we actually be confident that the summation as defined, the addition as defined, closes in this set. Problem is clear. Huh? Okay, so that's the idea. And now we're about to construct this. So, okay. Claim plus and S multiplication close in TPM, which is just to say this leads to TPM and the result is again an element of TPM. Now, proof. Construct the curve sigma as indicated down here, and then similarly do the same for the S multiplication, which is simpler. So how do we construct the curve sigma? Now, it's easiest to do this by employing a chart. So employ a chart u comma x, and the point of interest, so we have a tangent point at a point, a tangent space at a point P. The point P be part of that chart domain. Employ a chart ux and define the curve. The curve is sigma, and it depends on a parameter lambda, and it's built as follows. It is x inverse, so I take the inverse of the chart map, and here I take after, x inverse after, x after gamma plus x after delta. So gamma and delta are these two curves whose tangent vectors I want to add, minus x of p. Now this is a very funny looking definition. Let's first see whether it makes any sense at all. So the curve sigma, if it is a curve, it better go from some interval lying in the reals. So you see now, if one wants to be very precise, one needs to specify which interval, but talk about that in a second. In the reals, a curve that goes into M. Now, because we chose a chart, we only want to construct this over the chart, but let's not be so picky. So we want a curve in the manifold, and we have the curve gamma and delta given. Now, the curve gamma and delta, I represent them here by gamma. That's something like this. Is a curve, and now you only look at how it goes into this chart. So if you want to be precise, you only have the pre-image of u under gamma. You see, you can do this. And then you use the chart map here. You come to x of u, which lies in Rd. And now the key point is you can go this path. This is x after gamma. This is a map from some interval on R to Rd. So this is the chart representation of the curve in the real world. And the key point is that this here is a map from R, or part of R, into Rd. And this is a map from R to Rd. Well, strictly speaking, this is also a map from R to Rd, but it is the constant map from R to Rd. It always leads to the point x of p. Now, because these are maps from R to Rd, I can add them, because this addition is the addition on Rd. And so is this the addition on Rd, or rather the addition of the inverse element. Okay? So no doubt I can do this here. And what this means in pictures is I have here the real world, I have the point P, there's one curve gamma running through it, there's another curve delta running through it. And what I want to construct here is, if you think of the velocity of gamma and delta, well, we don't have an intuitive picture yet. The velocity is this funny directional derivative, but the idea is there needs to be another curve in the manifold whose tangent vector is the sum of these two tangent vectors. That's the idea. But we cannot add curves. I mean, the idea is a little bit like we want to add the curves or find the intermediate curve or something. We can't do this in the manifold because the manifold doesn't have enough structure. So instead, we choose a domain U, map this domain to a chart. So this is x of u, is part of the chart map. And in this chart, where you have your nice RD, in this chart, the first curve, oh, there's no color, okay. The first curve, say this is the point x of p, the first point runs through it like this, the other curve runs through it like that. And in the chart, you can take the coordinate representation of the images of the curves, x after gamma and x after delta. X after gamma, x after delta, and this point here is x of p. You can take the representatives and you can add the curves. Okay, and that is then this thing in brackets, and this minus x of p, that's the addition of the curves in the chart, and this minus x of p actually ensures that at parameter value lambda equals 0, the resulting curve really goes through this point as well. Okay, now you have a curve in the chart. Now that sounds very bad, okay? Because you know that the same curves you could represent by wildly different charts. You could choose such a different chart that what here the sum is this curve, you do something very crazy and the sum looks very different in another chart. So if we were to define the sum of curves as such, this would be very wildly ill-defined. Now, however, we seem to be doing exactly this, because then we take this resulting curve in the chart and we take this curve and lift it back up here to produce this curve. This is this x inverse, takes you up again. Looks wildly ill-defined. But what will save the day is that we will not be interested in the entire sum curve, we'll only be interested in its derivative. And the derivative will take care of all the stuff that will make the sum of curves ill-defined, but the sum of the tangent vectors, which is the first derivative to the curve at that point, that will be well-defined. Okay, so many words, but the question is, what is now the tangent vector here? So calculate. So far this is just a suggestion what we could do. So we calculate what is the tangent vector to the curve at that point. Well, in order to find out, we best apply it to some arbitrary smooth function f, and it becomes f after sigma derivative at position 0, because we have ensured here by construction sigma of 0 is again the point P, because it is, well, sigma of 0 is x inverse of x after gamma of 0, this is x of P, plus x after delta of 0 is also x of P minus x of P, is x inverse after x of P is P. So it is a curve through P at parameter value 0, fair enough. So the definition of the tangent vector of this strangely constructed curve is this guy. Okay, so now how do we go about this? Well, we plug in the definition of our sigma. So this is f after sigma, right? And sigma is this, is f after x inverse after, now it comes, x after gamma plus x after delta minus x of P. Close bracket from here, and then we have big brackets. Let me draw square brackets. Derivative at position 0. This is just plugging in the sigma. Now, again, it helps to look at the domains and the ranges of these maps. F after x inverse, that is, hang on, that's from RD to R. That's a map from RD to R. It's the chart representation of the function on the manifold. And this whole guy, we figured out before, is a map from R to RD, correct? Yes, from R to RD, and that's fine. You can take it R to RD, and then afterwards you do RD to R, that's fine, and then you derive the whole thing. So it's one such map after another such map, and that means you can use the chain rule for this derivative. You have a composition of two maps over RD to R and so on. You know the chain rule, and it's of course the multidimensional chain rule, because you can take the derivative in direction A, or the direction is the wrong word, the eighth partial derivative of this first function, f after x inverse, okay? And then you take this derivative of the eighth component of this guy. Well, what is the eighth component of this guy? This is, so first of all, you evaluate this at this point with the 0 plugged in. That's, of course, x of P that we know. Times, so I need a new line, and times normal multiplication. The derivative of the eighth component here. But what is the eighth component? The eighth component is xa after gamma plus xa after delta minus xa of P. Of this we take the derivative at position, at parameter value 0. Okay? Now, Yes?
Is there anything in between, like dots?
No, sorry. Yeah, the dots, well, yeah. Just suppose, yeah, I don't know, you don't need them, right? Okay. Okay. So this is just the chain rule, okay? But now, and this is now the beauty of the derivative and what I was talking about before, this is just a sum in the chart. But now you derive it, and because you derive it, this derivative now is linear, of course, so it acts on every factor separately. And it acts on the first factor to get you xa gamma prime, but this recombines with this guy here to f after x inverse after x after gamma prime at position 0. The second factor does the same thing. It recombines with f after x inverse after x after delta derivative at position 0. And the last one is, of course, 0 because it's the constant function. But now here, the x inverse in x, I mean, I freely use the associativity of the circ, of the composition. That's, of course, is f after gamma prime of 0. This is, of course, x gamma comma p and acting on f. And this back here is x delta comma p acting on f. Aha, but this is nothing else but our definition x gamma comma p circ plus x delta comma p, both acting on f. So we managed to show that indeed the sum of the two directional derivatives, or the tangent vectors to the curves gamma and delta in the same point p, indeed equals the tangent vector to another curve sigma, which we constructed here explicitly. Okay. So we have to pull this stunt of going to a chart and constructing the sum of curves with something terribly ill-defined. Well, but what is not ill-defined is the first derivative of it. That is independent of the chart map because the chart map cancels out again. And that's the trick. And indeed, the sum was the tricky part. So we showed the sum is closed. And the S multiplication is much simpler because there you just do the same thing and you write lambda times x after gamma or something like this. Lambda times. And you don't need all the rest. Okay, it's much simpler. Okay. But so this is the basic idea. So in fact, if you look back to the left part of the blackboard, could we have the camera back to the left one? If you look back here, then you see, in fact, it's a very simple definition of what a tangent vector space is once you accepted this definition of the tangent vectors being these linear maps. Because the addition and S multiplication is just the addition S multiplication of maps once you convinced yourself that it closes in TPM. But now that we know it does, we never need to care about this anymore. We always know there is the underlying curve, okay, for the sum and the S multiplication. Before we continue looking at properties of this of these tangent vectors, there is a little aside on algebras and derivations. So this is not derivatives, but derivations, and that's a technical term. And so the definition that we need is the following definition: a vector space V plus and S multiplication equipped with and now we call this a product, and this can take various shapes or forms. We'll meet several in the future, with a product, and let me call this product simply big blob. What is a product? With a product that is a bilinear map blob, which takes you from V cross V to V in bilinear fashion, is called an algebra. An algebra, which is therefore a quadruple, where you don't only have the S multiplication with respect to the underlying field, but you also have a product between the elements of the vector space. Okay? This is an algebra. And yeah, so there are various examples for products. In particular, we'll meet a Lie product, which is an anti-symmetric product. There's no assumption that it's symmetric. I mean, it's just a bilinear map, right? Or you already know from high school mathematics, in R3, you can establish the so-called cross product. Now, with this rule here, that's a product, and it makes R3 to an algebra. You can't do this on R4, okay? There are concepts that lead beyond that, but anyway, you can't do that. So anyway, here you have the algebra, and the example why I bring this at this point already is that C infinity M, which we recognized to be an R vector space, yeah, you can of course define a blob C infinity M cross C infinity M to C infinity M that sends a pair of smooth functions to the blob of the two smooth functions, where the blob is just defined pointwise. F blob G at a point F is just defined as f of p times g of p, and this is the multiplication in R. So it's the multiplication of two functions, whereas this S multiplication was only the multiplication with respect to a fixed constant. It's a different thing. It's structurally totally different. It's very important to realize this. So what we could therefore say, the C infinity M we defined is not only a vector space, it's even an algebra with respect to the obviously defined multiplication. Okay. So this seems formal overkill because we knew before how to multiply two functions, but the point here is to realize what the structural level of this whole thing is. So that's a K vector space. So now the next definition is that of a derivation. Definition. A derivation is a linear map. It's a linear map. So derivation capital D is a linear map D that takes an element of an algebra and sends you to an element of the algebra, which additionally, in addition to it being linear, which additionally satisfies the Leibniz rule. Well, this is just to refer to this rule in the future, the Leibniz rule, and that is you take, okay, I'm sorry. I should do this more generally, so not, well, this is the example we're going to use, but we can speak more generally of a derivation is a linear map from an algebra to an algebra, where this is an algebra. And this linearity here, of course, refers to the algebra being a vector space. Otherwise, we couldn't talk about linearity, but which additionally satisfies, now you guess it, if it's an algebra, we now need to have we have to have a rule that uses the blob. The Leibniz rule is that D acting on two elements of the algebra, which I may call F and G, you blob them, you get an element of the algebra again, and the question is, how does the D act on this? And the Leibniz rule stipulates that it acts like this, that you act with the D on the F and then you blob it into the G, plus you take the F and then you blob it into the DG. Now, of course, this terribly looks like the product rule from differentiation that you know. Yeah, that's true, because the normal differentiation, you know, is also a derivation. Okay, it's linear. You know that differentiating is linear. You call this the sum rule. But it also satisfies the Leibniz rule. You call this the product rule. Okay, but this is the abstract version of this, and this works in far more situations than just the one we use it here now. But I'll provide both examples. So example or examples. You can have this as the algebra, C infinity m plus times blob. And as a derivation, you take any x from a tangent space. So I no longer need to say to which curve, well, I don't need to say to which curve at which point it corresponds, because if it's an element of TPM, it's clear it's a curve through the point P, and there will be some curve that reproduces this x. Actually, there will be many, many curves that will generate as the tangent vector this one x from the tangent space, because I could have different curves running through the same point intuitively at the same speed, and they will produce, although they're different curves, they will give rise to the same tangent vector, right? But it suffices that I know there is some curve. So I take some element of the tangent space and I act with it on C infinity m. So any x I take, any tangent vector I take, of course, takes such a function. Okay. Hang on a second. So we have to. Okay, I have. I can generalize this and take a derivation from one algebra to another algebra. So I take two algebras, and then this will be the blob in the A algebra, and this will be the blob in the B algebra. Okay? You see, this is more general even than what I wrote down before. Okay? And now we take as the first algebra this, and as the second algebra, we take the vector space R over itself. I mean, all the blobs and the dots and whatnot here are the multiplication on R. So this is also an algebra, no doubt. Okay? And now this is a derivation because one can quickly check that xfg, where this is the blob in here, I don't need to write this down, so one can check that this is xfg plus fxg. And let's put this to the problem sheet. This is very straightforward, and you may have seen this before. So that means a tangent vector at the point P is a particular example of a derivation. Now you say this abstract view is really heavy machinery to say something very simple as this. But we'll later on, actually quite soon, we'll meet another type of algebra. Well, we'll meet several, but well, let me make another example. The other example is the following. You take, let A be the set of all m times n matrices. So a small a is m times, okay, nonsense. Let's take as the algebra the endomorphisms on some vector space V. Some vector space V. Okay, we take the endomorphisms. And now as this is just a vector space. Now we know that the endomorphisms over a vector space are again a vector space. So it's not quite an algebra yet. It's the vector space underlying the algebra. But now we can define a blob on the algebra, A cross A to A. Now we need a multiplication, a bilinear map. And it's defined as follows: a phi and a psi, so two endomorphisms on phi, are to be mapped to phi after psi minus psi after phi. It's obvious now the composition of two endomorphisms is endomorphism. It's a vector space, so I can add the additive inverse. This is again an endomorphism. Okay, so it lies again in A, that's fine. And if you want to, but this is really the definition by the left-hand side, you can give this guy the name square bracket phi comma psi square bracket, and you can read this as the commutator. But what's a commutator? A commutator is defined as the difference between the two compositions, abstractly. You don't need matrices or matrix multiplication, it's this composition, quite abstractly. Now this is the algebra, and you see that this kind of, so the blob has a different notation here. It has the notation of these brackets. But it eats two algebra elements, it spits one out. It's an example for an anti-symmetric algebra, an anti-symmetric product. Well, but we said nothing about the bilinear map being symmetric or so. So this is fine. So this is an algebra. So we have NV equipped with the addition and S multiplication, and this guy is an algebra. And people call this a Lie algebra. Aha. So you have an algebra. A Lie algebra is a vector space, yeah, equipped with a non-symmetric product. Well, actually in this shape, because it has a specific property, it satisfies the Jacobi identity. That's quickly calculated. So that is that phi comma psi comma rho, and then you take a product in the product, but how else than this? You take this plus, and now you cyclically permute psi comma rho comma phi plus rho comma phi comma psi. This sum is 0, and this really follows from this definition. Okay, so you have this. And so we have this algebra, and this is called a Lie algebra. So it's a special instance of a Lie algebra. Any algebra that satisfies the Jacobi identity is a Lie algebra, but this is one particular way to produce it. But now where's the derivation? Okay, so can now define a derivation. And the derivation, well, could be called D. Well, no, let's give it the name it has. It's H comma open slot. Well, if the bracket takes two elements of the algebra bilinearly, then leaving one slot open produces a linear map. All right? And so this guy I could call the D, okay? The D that's produced by the H, and this H is some fixed element of the algebra. Now, guess what? You take this D and you apply it to a product of elements of the algebra. So to A blob B. Well, the blob happens to be the bracket now. Okay, this is the D applied to the blob. And using the Jacobi rule that we just wrote down, it's very easy to see that this is the product of D applied to A comma B plus A comma the D applied to B. Well, but because the bracket is the blob, this is the Leibniz rule. If instead of the bracket I wrote the blob, D of A blob B is D A blob B plus A blob DB, you'd immediately see the Leibniz rule. And you of course know this kind of derivation. Where do you know it from? From quantum mechanics, or also from classical mechanics. Because in classical mechanics the Poisson bracket is also a derivation. On which algebra? Yeah, but the algebra is the functions on phase space, and that in classical mechanics, the functions on phase space you call the observables. The Poisson bracket in classical mechanics. Okay, so remark. The Poisson bracket in classical mechanics is a derivation on functions, on the algebra of functions. On phase space. We'll go the observables. And this and only this is the reason why in classical mechanics you can identify this derivative with this derivation. I mean, this must certainly satisfy, or if it acts on observables, must certainly give rise to the product rule, because it's just a derivative. Well, better this guy also gave rise to the product rule. Okay, so that's of course remark A. Remark B, quantum mechanics, d by dt is to be identified with h comma open slot, acting again on the observables, but now they're self-adjoint operators, ta 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 ta, you know. Okay, so this fact, this idea of derivation on an algebra satisfying the product rule, this is something you met in classical mechanics, you met in quantum mechanics, and now you meet it in differential geometry. It's an extremely common concept, and it's maybe worth once and for all clarifying its algebraic status. Okay. Now, okay, but my main point was that the tangent vectors are derivations. Okay. Are there questions so far? Good. So that's the end of the aside on algebras and derivations. Now we have an important theorem. We looked at the tangent spaces, or at the tangent space at one point. Of course, we could look at the tangent space at another point. And the tangent space is a vector space. And so as a vector space, it has a dimension. Dimension as a vector space. So this is the vector space dimension, which is given by the size of the basis in case it's finite dimensional. Now the theorem is that the dimension of the tangent space as a vector space equals the dimension of the manifold as a topological manifold. These are two entirely different notions of dimension, right? A vector space dimension has technically nothing to do with a manifold dimension. The manifold dimension was R to the D, the charts you go to, but the charts were not considered vector spaces, just RD, the topological space. Now, here, this is the vector space dimension, so in principle, they're very different dims. You could call one capital dim and the other one dim. So there's nothing obvious about this, and we need to prove this. Okay. Now, obviously, we need to relate this type of dimension to this type of dimension. So we will construct a vector space basis from a chart basis. Idea: construct a vector space basis from a chart. Okay. So let's make the usual preparations for this to set up such a proof. You choose a chart UX that contains the point of interest, the tangent vector space of interest. And now the idea now is, consider dim m many, bad English but very clear, dim m many curves, and these curves are called gamma A. I put this in brackets to not confuse this with any type of component of a curve. This is just the eighth curve, so A runs from 1 to dim m, such a finite set of curves that go from R to M in principle, but we just want them to go to U. And so then, well, we can write all of R. We write the pre-image of U under the curve gamma A. It doesn't matter. Such curves with the following property, that having chosen a chart, that the x, well, let's put the B, let's put this down here as an A, such that if you take the bth component of the chart map and you apply it after the eighth curve, that you then have a chart representative of the curve, right? This is now down in the chart, that has the very simple shape delta BA times T. So I choose very special curves who, in this chosen chart, have this simple form. Well, it's very clear what this is. You have your manifold M, you have your domain U, in which the point of interest lies. So together to this U corresponds, or together with it comes a chart map that maps you down here to RD. My illustration is, of course, R2. RD is the Cartesian product of D copies of R. So I have a very clear notion of the first component, second component, third component. I put here the first one, there the second one, and so on. And now, what is this? It means that the chart image xb after gamma is the eighth curve, has all components in the chart 0, but the eighth component, and that runs linearly, oh, I'm sorry, not t, linearly with the curve parameter lambda. So I chose a curve that up here may look like this, but down here looks like this, right? This would be the curve gamma 1, because this down here is x after gamma 1. This is this curve. And then I have another curve up here, which up here may look like this through that point. That will be the curve gamma 2. But it's only the curve gamma 2 if in the chart representation it looks like that. Okay? So in a sense, if you think about x inverse, I could have also started with the chart representations down here. And by x inverse, I could take the entire coordinate web here and go to the manifold and look for a given chart, what are the coordinate lines if I draw them on the manifold. That's the idea, but we're only interested in the coordinate lines through the point P. So this is kind of these curves, and this is the definition. Okay, this is this set of curves I'm looking at. It's a very specific set of curves, and clearly on the manifold, and it clearly employs a given chart to produce them. Another chart would produce another coordinatization. And this is what we've been doing all along. Maybe one should have drawn this picture quite in the beginning to get a better idea of the back and forth between the charts here and there, but that is what it is. Okay? So we got ourselves these very special curves, and once we have them, we can of course calculate the tangent vectors to these very special curve. Tangent vectors, so there is a number of those. Let's call them EAs, tangent vector EA, and this EA is nothing but another symbol for x gamma, what do we say, sub A? We said sub A, yeah, gamma sub A at the point P, but the point P, we saw all these curves gamma sub A, put this in brackets, at value 0 ran through the point P by construction, did they? Yes. Hang on, what did I write down? I wrote down that gamma A is such that xb after gamma A of lambda is delta BA lambda. That means at lambda equals 0, the value of this, I'm sorry, I'm a little confused, is the x0. Ah, okay. I should have written that I choose a chart centered at P. So using a chart centered at P, and this centered means simply that the x of P is the 0 in R dim V. So that the point P at which I have the tangent space gets the coordinates 0, 0, 0, 0, 0 in this chart. Now this is without loss of generality. Obviously, I could arrange for this by suitably subtracting coordinates like we did before. It's just terribly convenient to use a chart that's centered there. Let's do this. So good that I looked at this again. And yeah, and then it's indeed we calculate for each of these curves that we pulled up into the manifold, we can calculate in the manifold the tangent vector. That is what we always do. Okay. And now it's instructive to see how this eighth tangent vector, so the A, we have a number of such tangent vectors, how the eighth tangent vector acts on a smooth function. So f is a smooth function, of course. How does it do that? Well, it does so by x gamma A, comma P acting on f. Now this is by definition of the tangent vector. This is f after gamma A derivative at position 0. Right? This is this guy. And now we insert the chart. Well, we can first do this algebraically. This looks like this, x gamma A, derivative at position 0. I just inserted the identity, so to speak. And now I do what I always do in this case. I use the associativity of the circ, and I get del A f after x inverse. This is already using the, so this is at x of gamma A of 0, the chain rule, times, and then the eighth component of this guy. But what is the eighth component of this guy? This is xa. Sorry, I already have an A here, so I need to use another dummy index B. This A stays. And then it's the bth component, xb after gamma A, derivative at position 0. All right? It's just application of the definition and the chain rule. And now the first part, we're not going to change f after x inverse. That stays like this. It's to be evaluated at x of gamma A of 0, but that's x of p. Well, it's to be evaluated at x of p times. Now this guy we know better because we know underived, this is delta BA times lambda. That's what we defined. But so if I derive it with respect to the parameter, it's just delta BA that remains. At 0, well, that's delta BA. It's delta BA. Well, but that simply means it's del A, some rule and so on, f after x inverse, right? Yeah, well, that is what it is. Again, I emphasize, and maybe at first mysterious remark here, this is the 8th partial derivative of a function from Rd to R. In physics, we sometimes write, instead of this, we write d by dxa, right? Now, that makes absolutely no sense. Because if you have a function from Rd to R, this Rd is a d times Cartesian product of R. Now, you always know which is the first entry of this function, which is the second, which is, and so on, because the Cartesian product is the ordered, it's the tuples, right? So all you need to instruct me is whatever this function here is, if it's a function from Rd to D, you tell me derive with respect to the 8th entry, say the 3rd. Okay? Does it matter how I call this 3rd entry when I define the function? I can say this function fxyz, f of xyz is x squared plus y squared plus z squared or something. Does it matter how I call the 2nd entry, whether I call it y? No, I could call it b, then the function is defined with this b, but for the abstract derivative it doesn't matter. As little as it matters in one dimension for this derivative how I call any this x or lambda or whatever with respect to which I derive. It has nothing to do with the name of the independent variable. That's clear, right? It's the abstract derivative, and that it is what it is here. Now, why do I make so many words about this? Because obviously there would be no harm, one thinks, in writing d by dxa, well, I mean the 8th variable that appears here, and let's call him x1 to xd. Well, the harm is there where I now define a new symbol which much more deserves to have that shape. It's called d by dxa. It's an entirely new symbol, has nothing to do with this symbol, absolutely nothing. And it doesn't act on a function from Rd to R, it acts on a function f. Well, it's the f that's here, but recall that this f is a function from m to the real numbers. That's not a function from Rd to R. If I have a function from the manifold to R, I have no idea what it would mean to derive with respect to the first entry. The manifold is a topological space. What do you mean by the first entry? You first need to use a chart map to coordinatize the manifold around the point of interest where you derive it. Okay, so I should write here of x of p, and then one would say here this is the derivative at the point p, right? Or of p or something, okay? I first need to coordinatize, and then, well, how do I do this? Well, then I get a chart representative of this function on the manifold, which is then a function on Rd, and then I can take the derivative in the 8th direction. So, again, del A takes you from a function, from a smooth function from Rd to R to a smooth function from Rd to R. It always did, it always will. It's called the partial derivative, and it's an object that acts on functions from Rd to R, where the Rd implies an order of the entries. In contrast, d by dxa at the point P, it doesn't matter where you put the point, you know what I mean. At the point P, that's a totally different beast. Namely, it takes a smooth function on the manifold into R, but that's our definition of this object. And it takes this, well, at the point P, it takes this to a real number. If you did this here at a specific point, x of p, if you wish, it would also take you to a specific real number. Okay, let's look at it like that. Let's not produce the derivative function, but just the derivative at the point. Okay? Now you see the difference. Now for the manifold it makes perfect sense. No, it doesn't only make perfect sense, it's necessary that you picked a chart in order to derive with respect to the eighth something entry. But so whenever you see the symbol in this course, and I recommend to you in the future for your own calculations, whenever you write d by dxaf, the x is the x from the chart map. I mean, it's just a symbol, right? It's just a symbol, but this x refers to the specific choice of chart map by which you can think of the eighth component of a function. The whole thing is defined as this. It's the partial derivative. We know how to calculate this because this is just a symbol. Applied to f after the inverse chart map. It's the chart representative of the function. Okay? Very important to not confuse this. So my claim is you never so far needed this. You always needed this. And here it makes sense because it refers to a certain chart, which you need. Okay, so we have this guy. And so what we saw, in summary, the eighth tangent vector with respect to these very special curves, we can now write as d by dxa, if you want, at the point P, because this is the tangent vector at the point P. So but this is just meaningful because this symbol, if it acts on a function, which is what defines such a map, is defined like this. And this you can calculate. Okay? So these were the tangent vectors to these coordinate-induced curves are the tangent vectors to the chart-induced, coordinate-induced, whatever, curves gamma A. Now, what's their meaning? Why do I look at these specific curves and why do I look at their tangent vectors? Well, the claim is any vector, any vector x in the tangent space, TPM, can be written as x equals xa, but these xa's are just real numbers, xa times d by dxa at the point P. And there is a summation convention here. So we sum over these a's. In other words, the d by dx1 to d by dx dim m are a generating system for the tangent space. So let's see whether we can show this. And then, of course, the next step will be to show that they're also linearly independent. If they're linearly independent in their generating system, there are a basis, and because we have dim m, many of them, the dimension of the tangent space would be the dimension of the manifold. This was our claim, but you see in this constructive proof, there's much more technique and much more than just the proof of the theorem. Is there a question so far? Yeah?
Have you defined what delta BA anywhere? I mean, it's clear what it is.
Oh, yeah, no, I don't think I think I did before, but it is as always, delta AB is 1 if A equals B, and it's 0 else. That's again the same thing. It's just short notation for writing down an array of equations. Yeah. Okay. So now let's see whether we can do this. So proof of the claim. So there certainly exists a smooth curve mu in a manifold such that the arbitrarily chosen x, which I want to expand, is the tangent vector to the curve mu at the point P, through P, curve through P, such that I can represent this tangent vector by the tangent vector to the curve, because that's exactly the definition of being an element of TPM. There must be an underlying curve. There are many underlying curves that can reproduce this, but I pick one. I have one of those. And now the claim is I can expand this in terms of these special tangent vectors. Let's see whether we can do that. So x mu comma p. How do you study a map? You study a map by letting it act on an arbitrary element of its domain. That's always the clever thing to do. So this is, again, f after mu, in this case, derivative at position 0. So all the provisions from before, namely, for instance, that mu at parameter value 0 goes through p, we always make the same assumptions here. F after mu prime 0. So now, again, we insert the chart, and it's, of course, the chart with respect to which we build these special curves. So we take f after x inverse after x after mu prime 0. By the way, if you wonder, is it first the x and then the x inverse, you can always draw your little pictures. This is a curve, and this is a function. And if you restrict this to a chart map, well, then maybe here you have the pre-image of the curve of the domain, tralala. Then you have the chart map. You go to x of u. This is a part of Rd. And then you construct the representative of the curve is x after gamma. And you construct the representative of the function. This is f after x inverse. So they come in these pairs. Okay? So you can either do gamma after, mu, sorry. Mu, we called it mu in this case. You can do f after mu, or you can do this combination, f after x inverse after x after mu, and then you can drop the brackets because of the associativity of the composition. Okay, so just these diagrams are always very useful. Okay, so you might think of them. Okay. So, but now it's pretty obvious what happens here. We again do the chain rule. You see, it's the same calculation over and over again. You do the chain rule. You evaluate at x of mu of 0 is x of p. This is at x of p times. And now here you take the eighth component. Well, again, I probably want to take the bth component. xb after mu inverse evaluated at 0, but this gentleman here, we know this is d by dxb acting on the manifold function f rather than the chart representative of f, evaluated at the point p. But there's our result, because you can write this as xb after mu derivative at point 0. What is this? This is for every b, this is a number, right? For every b, this is a number, times d by dxb. Now I put the p down here by notation, and this acts on f. And there's a sum rule here, a summation convention. So I can put, I don't know, big brackets around it. And now you can compare. You have, well, I even box it. I box it, and I box this, and you see, aha, every x mu p, which is any x in TPM, can be written as some linear combination. I even constructively found which linear combination of these tangent vectors to these chart-induced ones. Now, these guys, of course, are the components with respect to this generating system. Okay? I almost said basis, but we haven't shown that yet. Okay? And we'll come back to that, because that is what you always did in physics. You took a curve, but you didn't take it in the manifold abstractly. You didn't take it in the real world. You took it in a chart representation. You said the particle flies along the curve mu, and the first component is this function of time, the second component is this function of time. That's your curve. And you see, you derive every component. Component-wise, you define well, the components of the tangent vector, physically speaking, the derivative. But they were the components with respect to what basis of the tangent space? Well, with respect to the chart-induced basis. But because you usually always took RD as the basic space, and then you could identify every tangent space with this RD itself, it's usually muddled up what is what. But this is the real logic behind it. Okay, so thus, indeed, the d by dx1 to d by dx dim m, and if you're very careful, you say they act, but then they evaluate at p. This set is a generating system of TPM. Of course, there are many others. You could take this basis, this generating system, you build linear combinations of certain types, and you get generating systems. So it's not unique. No, it's a very special one induced from the coordinates, but it has this advantage. In coordinates, I can calculate the derivatives to curves in the chart picture, so it's very useful. We will have opportunity later to consider bases to a tangent space that are not coordinate induced, especially if we look at, well, at a point it can always be constructed from coordinates, but if you look at extended regions, vector fields and so on, it can be advantageous to not look at coordinate induced basis fields, but we'll come to that later. Okay, so this is technically very clever. So now show that they are linearly independent. How do we do that? Well, we consider lambda a d by, well, this is a different lambda, I should call it differently. You know how that works. D by dxa at the pth point, and we assume this is 0, and if they're linearly independent, we should be able to show that every of the lambdas is 0, right? Now, how do we show this? Well, again, this is a tangent vector. I mean, it's an element of a basis of TPM, so in particular, it's an element of TPM, for each A. An element of TPM are the tangent vectors, but the tangent vectors are these linear maps. They are the directional derivative operator. So this is actually an operator equation. How do you deal with this? Again, by letting it act on an arbitrary object in its domain. That's how you get a good handle on this guy. Now my question is whether I wanted that. Yeah, okay, very good. So in order to show linear independence, however, I now let it act on a number of very specific functions. And there will be some words to be said about this. I will let them act on the functions xb. There is the immediate question, is this legal? A lawyer will always tell you it depends. That's the safe answer. No, the answer is yes, it is legal, but it's not so obvious. Why is it not so obvious? Well, let's look at this. So the x's, this is the chart map, the components of the chart map. The chart map is this kind of guy, you remember? And what do we know about it? We know about this chart map that it's a homeo. It's a homeo from U to its image. It's continuous, invertible, all that kind of stuff. And so from that it follows that the bth component of this is U goes to R, some part of R, well, some subset of R, so some subset S of R. We know that the components of a homeo are homeos, essentially because the product topology on RD is the same as the standard topology, whatever. I think the last problem on the last problem sheet kind of used that too. Okay, so we have these No, homeo can't be true. I'm sorry, this is not homeo, this is continuous. That's certainly true. It's continuous, right? Can't be homeo because this is higher dimensional than this, but it's continuous. Continuous map. Now, can I act with a derivative operator on there the way we define it? The answer is no. At first, no, because this was defined to act on C infinity m, on the smooth functions, but the components of the coordinate maps, by construction, they're continuous. They can't be more than continuous because this is on the manifold. I wouldn't even know how to say that this guy is differentiable. Well, but they are smooth because how would you, the same problem you have with any function f. For any function f, you could look at it on U to R. So that's now, well, I should write it here. For any f that's defined on the manifold, you can look at how it maps to R. So I don't need this subset here, how it goes to R. And here, very well, we can say whether it's smooth or not, because we decide this by choosing a chart map X, this is an X of U. And we say that, if this is f here, we say that if f after x inverse is smooth, then the f is called smooth. But now it's simple, because if I apply this to the bth function of the component map, so in order to decide whether it's smooth, in addition to it being continuous anyway, I take the chart map, I land at x of u, and here I'm at xb after x inverse. But what is this guy? Well, this lies in Rd, this lies in R. So xb after x inverse of a tuple here in Rd, let's call it A1 to AD, that's the coordinates here if you wish. This is, you go back and then you go back to the bth one, well, that's the projection map to the dth component, so this is simply AB. You pick out the bth component, or xb after x inverse is the projection to the bth component. And of course, this projection to the bth component is smooth. Of course it is, right? That's very clear. And because this definition in general is well defined here, that means, yes, it is legal. And you could say this definition of smooth, what a smooth function is, in particular is chosen such that any chart component maps, coordinate maps, are rendered smooth. Okay, so this is a little aside. It's a favorite for an oral exam, right? Because at first this can be very confusing. Okay, so this is a very big thought on this. Okay, so we can act on all of these. Now that we ensured that, we'll do it. So lambda a d by dx a acting on xb is assumed to be 0. Well, first of all, we look at the left-hand side. What is this? Well, we can practice now. So this is at a point P. What does this symbol and this action mean? Well, it means that you take the eighth partial derivative, you take the function on which you act, in this case the bth component function, and you compose it with the inverse of the chart map. So this x here says you put the x inverse here. This a here says you put this a there. And this xb here says you put this xb here. Not sure this makes it look better, but so this is the definition of this symbol. Okay? Now, but yeah, now you know what this is. So this is evaluated at the point x of p. That's the full thing. Now, but you know this is the bth component of this. You derive it with respect to a. This is nothing but delta a b. Right? take the bth component of this and then you derive it with respect to the eighth component. Well, but this is like the projection map, so it gives 0 everywhere apart from the eighth component where it gives you the identity. So it's delta BA. But that means that the whole left, so this is the equation and this is the whole left-hand side. So the whole left-hand side is lambda B, because you have, of course, the summation convention here, right? It's lambda B. Well, there you go. You're done. You start on the assumption that this guy is 0, so as an operator. So in particular, it must be 0 if it acts on particular functions. We picked clever ones. We derive lambda B is 0. Lambda B is the left-hand side is 0. Okay. So hence, d by dx1 at p dot 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 to d by dx dim m at p is a basis of TPM. And that proves the theorem. Questions? So terminology. So if, well, it's trivial, right? XA, if a vector X in TPM can be written XA, or is written, can always be written XA d by dxa p, then the real numbers x1 to x dim m are called the components of the vector x in TPM with respect to the tangent space bases induced from the chart u comma x, where of course the point P must lie in there, in this U. And on the problem sheet, I shall ask you to study change of components under a change of charts. It's of course a very obvious question. And the key issue there, I mentioned here for completeness, will be you can of course have a chart transition map that's highly nonlinear. I mean, you can go from Cartesian to polar coordinates. It's a highly nonlinear function. But at any given point, this highly nonlinear chart transition map, which is a function from RD to RD, will induce a linear transformation on the vector space at a point. And it must, because vectors need to transform linearly. Okay? If you have a chart transition map where you go to a new chart y, which in terms of the old chart x is given as, well, this is physicist notation, ya is ya of x1 to x dim m, but you know what I mean, you go from one chart to the other chart, then the linear transformation dya by dxb this can be evaluated at the point x of p. This point in Rd, this linear transformation will govern the change of chart, the change of basis on TPM. If you go from one coordinate-induced chart to another coordinate-induced chart. And because, I mean, this derivative, you know, this, what's this, the Jacobi matrix, of course, is again a function. I mean, it depends on several functions, is a square array of functions. But you evaluate at this one point x of p, and that will correspond now, kill me, I don't know whether it's the matrix A I wrote down last time or whether it's the matrix B I wrote down last time. But it's, in any case, it's this basis transition map. And you see, this is the full point of what I'm always talking about there are no position vectors. Because the position is this. Now, the position in a chart, if you want to assign a collection of numbers as indicating the position, you're talking about a chart. Because on the manifold, a point is a point. What are the coordinates of Paris? There are no coordinates of Paris unless I choose a chart and then look, it's 7, 2, okay, in a particular chart. But then you can change charts in any diffeomorphic way. They just need to be a C infinity from Rd to Rd function. You can change chart. It can be highly nonlinear. Now, these components, which are actually the coordinates, the components of the chart map, but they're certainly not components of a vector, because if they were components of the vector, they should transform under change of chart linearly, but, well, they don't want to. They transform highly nonlinearly if you wish, if you go to another chart. But the tangent vectors to curves, they're totally unimpressed by the high nonlinearity of the chart change. They only see at the point the Jacobi matrix evaluated at that point as the linear transformation map, array, whatever, that changes the basis on the tangent space. So in the old books, people said a vector is what transforms like this. A vector is whose components transform by this or by the inverse, okay? Depending on whether it's the A or the B. You figure this out. I don't even remember which I called A and B last time. But the vectors transform according to this. Well, but positions simply don't. Okay? Now, only if you restrict attention to linear changes of coordinate system, then of course, if this is a linear function, the new YAs of the old x's, then this transformation coincides with this one. That's very, very obvious, right? I mean, if you then put in another YA. So only if you artificially say, I always stay with one coordinate system and at most linear transformations, linear changes of chart, then you can yield to the illusion that also the components, the coordinates, constitute a vector that transforms linearly under change of chart. But then you say you can only do Cartesian coordinates and you can never go to polar coordinates, let alone any other coordinates that are slightly more interesting. The point is, it's just you delude yourself into thinking that positions, components of positions combine into a vector. And much of special relativity is done with this confusion. So people say, well, you have these very special linear transformations, the Lorentz transformation, they act on all of position space. The x mu's are being transformed. No, they're not. The x mu's you can transform any way you wish, and only the derivatives, that's the tangent vectors at specific points, they will transform. Of course, if this is highly nonlinear, then in the tangent space at P, the transformation will not be the same as the transformation at the point Q. You see? So these linear transformations will, if this is nonlinear, these will differ from point to point, from tangent space to tangent space. This is different if they're linear, then they're everywhere the same. Okay? But we should never abuse this by arbitrary restrictions of these functions only to save our concept of a position vector. It's an artificial concept. It's pointless. It causes confusion. Okay?